Hello guys, I'm here to uh, derive the Schrodinger equation. That's the time-dependent Schrodinger equation, the STD. So Schrodinger equation, it's an equation back in the 1920s. It was developed by somebody by the name Erwin Schrodinger. He was an Austrian physicist. So Schrodinger equation was developed due to some limitations in classical physics, which were not able to failed. It kind of failed to explain phenomena over the atomic scale. Things like stability of atoms, discrete energy levels in atomic spectra, etc., etc. So due to such limitations, then that's what made the Schrodinger equation to be brought up so that it can cover for such limitations. So let's dive in without much further ado. Okay, this is the Schrodinger time-dependent equation, the STDE. So this particular equation, it's dependent on the de Broglie wave equation, which is lambda is equals to Planck's constant all over momentum. Then continuing, there's psi, there's psi, which is symbolized by the wave function. That's symbolized. It's a symbol of the wave function. Sorry for that. Then just a minute. Then this is psi. That's the symbol for wave function. So this is psi for wave function. Then this is the formula for the Broglie's wave. So this is the wave function that represents matter waves or the de Broglie's waves. Then continuing, we are having k, that's constant of deriving the Schrodinger's equation, where k is equals to 2 pi all over lambda. When we change that, then we will be having 2 pi times momentum all over Planck's constant. Remember, lambda is equals to Planck's constant all over momentum. So replacing lambda with Planck's constant all over momentum, then we will be having this. Then in continuation, then starting with the wave function, we want now to define the equation of it for a particle moving freely in positive x direction. Remember, the applications of this is like the infinite well. That's the infinite well, where the wave function tends to a certain function, any function like x tends to a, and etc., etc. So it's always believed that that's kind of a fundamental application that easily explains what Schrodinger equation entails. So deriving the wave function, then psi is equals to a is just a constant, then multiplied by exponential negative I into omega t minus kx, close the bracket. Let's mark that as equation 1. That's the first equation. Then in continuation, then omega, we know that omega is 2 pi f or v, representing frequency. In replacement of that, then it's 2 pi e all over Planck's constant, where e is equals to vf or hv. Sorry for that. Then continuing, Planck's constant, it's always that. Then E is the energy, V all over F, V or F, that's the frequency. Putting the values of omega and k in equation 1, then we'll be having psi is equals to a exponential negative I into 2 pi Vt minus 2 pi over lambda multiplied by x. In continuation, then psi is equals to a exponential negative I, 2 pi. So we are ousting the pi out of the bracket because it's similar on this and this. So 2 pi into e all over Planck's constant. T. Remember, this is due to the frequency that is there, and the frequency is equals to energy all over Planck's constant. So energy all over Planck's constant multiplied by T minus momentum all over Planck's constant multiplied by X. Then coming to that, then we'll be having psi is equals to A exponential negative I 2 pi multiplied by this, which is also again a repetition of what. Then we'll again remove the Planck's constant because it's similar. So on removal of the Planck's constant, we'll have this equation. Then in continuation, we'll change Planck's constant. We'll replace Planck's constant with the h bar, which h bar is equals to Planck's constant all over 2 pi. So we'll have something like this, marking it as equation 3. So in continuation, then we will be differentiating equation 2 twice. Remember, equation 2 is sorry, this was equation 2. Sorry for that. This was equation 2. So we will be differentiating this twice. We'll differentiate it twice with respect to what? To x. So we'll be differentiating it twice with respect to WRT x, with respect to x, because there's a Schrodinger time dependent. So we'll be differentiating with respect to x twice, whereby differentiating it, we will be having the first differential, we'll be having delta psi all over delta x is equals to A multiplied by negative I P all over h bar into exponential negative I over h bar into exponential T minus momentum times x. The second differential equation will be this, whereby that's A multiplied by that. So remember, I, so because of the negative, so it will be positive I times P into that, then squared, then this one. So into continuation, we'll be having the final equation as this one. But now, this particular part represents the psi x. So that's the psi x, or the psi. That's the function of the psi. So replacing psi into that, then we'll be having this one. So it will be delta squared psi all over delta squared x squared is equals to negative momentum squared all over h bar squared multiplied by psi. Then into continuation, we want to make this one momentum squared psi subject to the formula, so that we'll be having this. We are going to use it later. So let's mark this equation 3. Then into continuation, differentiating equation 2 once with respect to t. Remember, equation 2 was this one. So we want to differentiate it once with respect to t. So on differentiating it, then we'll be having delta psi all over delta t is equals to negative I all over h bar A E exponential negative I into h over h bar into et minus px. Then delta psi all over delta t is equals to negative I all over h bar E multiplied by psi. E psi is equals to this, whereby into continuation we'll mark it as another equation, because negative 1 divided by I is equals to that. So we'll be marking it as equation 4. So equation 3 and 4, this equation and this one, we'll be replacing it in the total equation, whereby let me just show you that. We'll be replacing it in this particular equation, whereby total energy is equals to kinetic energy plus potential energy, whereby kinetic energy is equals to momentum squared all over 2m, that's 2 times mass, then plus v into xt, multiplying by this one, then we'll be having exponential psi is equals to this one. Then we run to replace the p squared psi and the e psi with equation 3 and 4, whereby while replacing that, then we'll be having the one-dimensional Schrodinger time-dependent equation to be this one. So this is the final Schrodinger time-dependent equation. Thank you very much. Subscribe to my YouTube channel and